Hello, everyone. Welcome, welcome, welcome to our great class. Um, you guys are great, and so it's always fun to see your faces. Please, if you don't mind, turn on your camera. I would appreciate that. I always love to see all of you. So it's a small substitute for seeing you in person, but hey, take what I can get. Right? This is where we are, and things are looking up. I saw Biden announce yesterday that there'll be vaccines for everybody by May. Wow, that'd be great. We all get vaccinated and we get back to real class. Yeah, that'd be fun. I can't wait, to be honest. But anyway, you guys have been real troopers throughout all of this, and I just can't tell you how much I appreciate each and every one of you. So thank you so much. I see the work you're putting in, and I see your faces and I see your understanding, and it's very, in spite of the situation, it's very satisfying for me. So thank you so much. We are in the middle of our acids and base chapter, and so we will continue that today. But before I start, I want to see if you have any questions. As you guys probably, I don't know if this is on your radar, but as you probably are aware, we have one more chapter to cover, and then it'll be the next exam. The date is March 18th. All right. So put that on your calendar. March 18th will be the second exam of the semester. Okay. All right. I don't see any questions. So let's go ahead and get started here. Remember when I showed you the list of weak bases, we saw bases like the bicarbonate ion, right? HCO3 minus. And I said the bicarbonate ion acted as a weak base. Well, the first thing you should understand, and I know you already know this, but negative ions like this don't exist on their own, right? So you're never going to find just a beaker full of bicarbonate ions, right? Why is that? Because if you have all that negative charge and no countering positive charge, right, it would be crazy, right? It would be like sparks flying all over the place and just like absolutely nuts, right? You can't have a whole lot of negative charge without countering that with positive charge, right? That happens in thunderclouds, right? Charge gets separated in thunderclouds, and as a result, you see lightning and thunder, which is that charge recombining. It gets separated by the action in the thunderclouds, all right? But typically, you don't just see negative charges and positive charges, you always see them together. So bicarbonate ion doesn't exist by itself. Usually it exists with some counter ion like sodium, for example. And we have things like sodium bicarbonate, right? Which is the active ingredient in baking soda, okay? And baking soda is basic because when you put baking soda in water, like all ionic, like all soluble ionic compounds, it decomposes, right? And it forms sodium ions and bicarbonate ions, right? And then this bicarbonate ion acts like a base, just like every other weak base. And do you remember our weak base equation, right? Number 2 of our two very, very important equations, right? When you have a base, reacts with water, right? And it's in equilibrium with OH minus plus BH plus, right? So the bicarbonate ion follows this pattern, HCO3 minus plus H2O. Now, the only difference here is that in this case, the generic equation, the base is charge neutral. But in the case of the bicarbonate ion, it has a minus charge, right? So when it picks up a proton, instead of going to BH plus, right, it goes, instead of being a positively charged conjugate acid, it is a neutral conjugate acid, right? So the conjugate acid is H2CO3, right? And it forms HOH minus. But can you see the parallel between these two equations? Everybody? Nod your head if you can see that. Awesome. Okay. So we want to see now how many kinds of ions can act as acids and bases. Okay. So whenever you see an ionic compound, hidden in that compound could be an acid or a base or both, because the ions can act as acids or bases. All right. Now, when you're examining on a compound, you want to look at the anion and the cation separately. Okay. The anions can act, an anion can act as a weak base. Okay. Remember what an anion is, right? An anion is negatively charged. Okay. So when you look at a compound, you look at the anion and you ask yourself, is this anion a weak base? How do you tell? Well, every anion can be thought of as the conjugate base of an acid. All right. So for example, Cl minus, right, is the conjugate base of HCl, right? Similarly, F minus is the conjugate base of what acid?
HF.
HF, right? NO3 minus is the conjugate base of what acid?
HNO3.
Right. You just add a proton, right, to whatever the anion is. The acetate ion is the conjugate base of acetic acid, right? And so on. So think of any anion you want, add a proton, and that anion is the conjugate base of that acid. Okay? Does that make sense so far? All right. So in order to determine if this anion is a conjugate, is itself basic, you want to ask yourself a question about its corresponding acid, right? You got to ask yourself a question about the corresponding acid. And it goes like this. An anion that is the conjugate base of a weak acid is itself a base. Okay, an anion that is the conjugate base of a weak acid is itself a base. But an anion that is the conjugate base of a strong acid is pH neutral. All right. So let's look at, I'll do it with my pen. Let's look at the anions that we wrote right here, and let's classify them. Cl minus first. It's the conjugate base of HCl. What do you know about HCl? Is it a strong acid or a weak acid?
Strong acid.
It's a strong acid. So what do you know about Cl minus?
Neutral.
pH neutral.
pH neutral. Okay. So Cl minus is not a weak base. All right. F minus is the conjugate base of HF. What do you know about HF?
It's technically a weak acid, right?
It's a weak acid.
Yeah.
So what do you know about F minus?
It's base.
It's a base.
Base.
Okay. So this one is a weak base. Okay. How about NO3 minus is the conjugate base of HNO3. So what can you tell me about NO3 minus?
pH neutral.
pH neutral. Okay, pH neutral. C2H3O2, the acetate ion, is the conjugate base of acetic acid, HC2H3O2. HC2H3O2 is what?
Weak acid.
Weak acid. So the acetate ion is a
A base.
weak base. Okay. And how does this act as a weak base? According to our good friend, the weak base equation, right? So if we had to write an equation for this acting as a weak base, we'd write C2 H3O2 minus aqueous plus H2O in equilibrium with OH minus aqueous plus HC2H3O2, right? Always follows that same pattern. That's why this equation is so important. We'll be using it over and over again, okay? Just like the weak acid equation that we talked about earlier. All right, does that make sense? Okay, so let's practice a little bit. Br minus, is it, now remember, these are all negative ions, so we don't have to worry if a negative ion is acidic. We just have to worry if it's basic, okay? So let's ask ourselves about each one of these. Is Br minus basic, yes or no?
No.
No, right? Why? It's the conjugate base of the strong acid HBr, right? HBr is a strong acid, so Br minus is pH neutral. How about NO2 minus?
Yes. Weak
Yes,
base.
that is a weak base. It's the conjugate base of HNO2, nitrous acid. Nitrous acid is a weak acid, so NO2 minus is a weak base. Yeah? What about NO3 minus?
Neutral.
Neutral or weak base?
Neutral.
Neutral, right? It's the conjugate base of HNO3. HNO3 is a strong acid, so NO3 minus is neutral. What about CO3 2 minus?
Weak base.
Weak base. It's the conjugate base of HCO3 minus, which is the conjugate base itself of H2CO3. H2CO3 is a weak acid, so both of those ions are weakly basic. Okay. Taylor, do you have a question?
Yeah. So for the rule, it doesn't specify how strong the base is. Do we assume it's always a weak base, or can it be a strong base too?
No, it's always a weak base. It's always a weak base. Yeah, and we'll figure out how to get Kb for the base in just a minute. So then we can figure out how strong it is, and we can find the pH of solutions containing that base.
Okay.
Okay, so we'll get there.
Okay. Thank you.
Okay, so anions can be weak bases. Cations can be weak acids. All right. So cations fall into where am I here? Let me see. Hold on. Oh yeah, okay, so that's there. Sorry, I just needed to see where I was. Just 1 second. Sorry about that. Okay. All right, here we go. So cations is weak acid. There are basically, actually, not basically, there are acidically 3 types. No pun intended. So cations as weak acids, 3 types. The first type is a cation that is the counter ion of a strong base. Cation that is counter ion of a strong base is pH neutral, right? So remember, the strong bases we talked about are the group 1 and group 2 metal hydroxides, right? So things like K+, strontium 2+, Na+, right? They are the counter ions of things like KOH, SrOH2, NaOH. All right. Since these are all strong bases, these are all pH neutral. Okay. So if you recognize the cation as a counter ion of a strong base, then that ion is pH neutral. All right. 2. Cations that are the conjugate acid of weak bases are weak acids. Okay. Cations that are the conjugate acid of a weak base are a weak acid. So for example, NH4 plus, right, is the conjugate acid of NH3. What do you know about NH3? NH3 is a weak base. So NH4 plus is a weak acid. All right. Things like CH3NH3 plus is the conjugate acid of CH3NH2. All right. Remember, these nitrogen-containing organic compounds tend to be weak bases, right? So the conjugate acid of them, conjugate acids of them are weak acids. All right. Okay, good. So let's see. 3 types. Cations that are cations of strong bases are not themselves acidic, right? So those include things like that. Cations that are conjugate acids of weak bases are acidic. So these here are all acidic. And then lastly, the third category is cations that are small, highly charged metals. Highly charged metal ions. Things like Al3 plus and Fe3 plus. All right. So by small, highly charged metals, I mean metals that are towards the top of the periodic table and not towards the bottom. All right. And ones that have big charges like 3 plus. Okay. And these are also acidic. Now, you might wonder how these work like acids. And the mechanism is a little bit complicated, and I'll show it to you, but don't worry about it. It's not that big a deal. But basically what happens is that these small, highly charged metals will bind to water like this. And then what will happen is that they'll react with water, and one of the water molecules will give up a hydrogen to that water and form the hydronium ion. Basically what happens is that these small highly charged metal ions withdraw electron density from the water, making these hydrogen atoms more acidic, okay? And that produces the acid. Don't worry too much about this mechanism. Just know that if you have a solution that contains these types of ions, that solution is going to be acidic, okay? Small, highly charged ions, okay? I see a couple of questions. Ryland.
When we say something's neutral, do we mean just 7.0 on the dot? That's the only neutral thing, or is there
Correct.
like?
Correct.
Okay.
Yeah. As long as there's nothing else in the solution, right? So for example, if I have a sodium chloride solution, right? The cation is pH neutral, the anion is pH neutral, so a solution of NaCl is pH neutral, unless it contains other impurities. Yeah? Emily.
Could we go over one more time? How do we identify a strong base? Were we given a list for that? I can't.
Yes. Group 1 strong bases are group 1 and group 2 metal hydroxides, right? So group 1 and group 2, these guys, when you put those together with with a hydroxide, those are the strong bases. Okay.
Okay. Thank you.
Yeah. All right, very good. So let's see how we're doing here. What can we say about Na plus? Will that be, so now we're looking at cations. All of these are cations. And remember, keep in your mind, cations, you just have to ask yourself, are they acidic? Anions, you have to ask yourself, are they basic? Don't worry about a cation being basic or an anion being acidic, okay? If it's positively charged, it might be an acid. If it's negatively charged, it might be a base. But you don't have to worry about the other possibilities, okay? So these are all cations, so we have to ask ourselves, are they acidic? So Na plus, is it acidic or neutral?
Neutral?
Neutral, right? Because it's the counterion of sodium hydroxide, which is a strong base. CH3, CH2, NH3 plus,
Acidic?
acidic, right? It's the conjugate acid of a weak base. So the conjugate acid of a weak base is itself an acid, a weak acid. Ba2 plus,
Neutral?
neutral, right? Barium hydroxide is a strong base, so barium 2 plus is neutral. Vanadium 3 plus,
Acidic.
acidic, small, highly charged metal. Okay. Yes, 3 plus is the most common. I don't think there are any even above that. It's just pretty much 3 plus. Okay, so let's go through this whole list. Now these are compounds, and we want to decide for each compound, is it acidic or basic? Okay. When you have a compound, you have to look at both ions, right? Because all of these ionic compounds, when they go into water, right, they ionize, they dissociate into their ions, right? So let's start with sodium chloride. What can we say about Na plus? Now that's a cation, right? So is it neutral or acidic?
Neutral.
Neutral. What about Cl minus?
Neutral.
Neutral. It's the conjugate base of a strong acid, HCl, so it's neutral. So what do we know about NaCl?
It's neutral.
It's neutral, right? So if I just have salt water, it's pH neutral. Okay. Sodium fluoride. What do I know about Na plus?
Neutral.
Neutral. What do I know about F minus?
Mild acid or weak acid, I think.
Basic is
Weak base, right?
Weak base.
F minus is the conjugate base of HF. HF is a weak acid, so F minus is a weak base. Okay, so what can we say about a solution of sodium fluoride?
Basic.
Basic. Yep.
Yeah.
Perfect. Okay, calcium nitrate, Ca2 plus, acidic or neutral?
Neutral.
Neutral. NO3 minus, acidic, neutral or basic?
Neutral.
Neutral. So what can we say about calcium nitrate?
Neutral.
Neutral. Okay. Potassium nitrite, K plus, acidic or neutral?
Neutral.
Neutral. Sodium fluoride, NaF, we said was basic, right? Because of the F minus ion. Potassium is neutral. NO2 minus, is it neutral or basic?
basic.
Basic. It's a conjugate base of a weak acid, so it's basic. So potassium nitrate is basic.
Mhm.
Potassium bromide, let's see. Potassium plus, acidic or neutral?
Neutral.
Neutral. Br minus, neutral or basic?
Neutral.
Neutral. So KBr is neutral. All right, is this making sense? Calcium acetate. What can we say about calcium? Acidic or neutral? Calcium 2 plus.
Neutral, isn't it?
Neutral. Yep. C2H3O2 minus, neutral or basic?
Basic.
Basic. It's a weak base. So this is basic. Iron 3 chloride, Fe3 plus, acidic or neutral?
Acidic.
Acidic.
Acidic, small, highly charged metal, right? Cl minus, Neutral or weak base?
basic,
Cl minus is the conjugate base of HCl. HCl is a strong acid, so Cl minus is
Neutral.
neutral. Neutral. So this solution would be acidic. Okay. Iron 3 fluoride. We know that iron, just like we talked about, is a weak acid. What about F minus?
It was basic,
Base.
right?
It's a weak base, right? So now we have a weak acid and a weak base. So we can't really tell for that one without more information. Okay? Because you have both present in that compound. Ammonium nitrite. What can you tell me about the NH4 plus ion? Acidic or neutral?
acidic,
Acidic, right? It's the conjugate acid of a weak base, so it's acidic. How about NO2 minus?
basic,
Basic. It's the conjugate base of a weak acid, so it's basic. So again, here we can't tell. Okay, because you have both present. If you have both present, you would need further information. I'm not gonna, there is a way to figure that out based on Ks and Kbs, but I'm not gonna worry about that, okay? I just want you to be able to tell whether just by looking at it without any more information, if the solution would be acidic or basic or neutral, okay?
So if we were asked something like that in the homework or an exam, we would just say, like, need more info, or can't?
You can't tell without more information.
Okay.
What you'd have to do is you have to compare the Ka and the Kb, and I'll show you how to do that in a minute, but I won't ask you that on an exam.
there was a problem like that on the problem set, and I think they just made us classify it as basic. But they like didn't
Yeah,
explain
well,
how to
you
do
can,
it.
you can compare, what you can do is you can compare the size of Ka and Kb, and then whichever one has the larger K, that's what would determine it. Okay, and you'll be able to do that, but I'm just not going to ask you that on an exam. There might be a problem on the homework that asks that. Okay. All right, so here's a question for you to try just on your own with a poll. Let me just start this poll. All right. Okay, I'm going to end the polling here. So throw in your choice. All right. That didn't go as well as I'd hoped, but that's okay. We can go over it. The correct answer is E. All right. So let's go through those really quick. So remember again, here's what you do. You got to look at the anion and the cation separately. All right. So let's start with the first one. Let's go through each of these since this obviously didn't. A lot of you still don't have this idea, and this is a super important idea. You got to get this concept down. So what you do is you take a compound like this, which you recognize as an ionic compound. NH4 plus is one of those polyatomic ions from first semester, right? So maybe you need to go back and look at your table of polyatomic ions from first semester and refresh your memory on those. But the two ions here are NH4 plus and Br minus, okay? And so you got to ask yourself about the cation. Is it an acid? Is it a weak acid? And the anion, is it a weak base? Okay, it's always going to be that way. Positive ions, you're always going to ask, is it a weak acid? Negative ions, you're always going to ask, is it a weak base? So then you look at NH4 plus and you say, I recognize NH4 plus because NH4 plus is the conjugate acid, right, of NH3. Okay, and NH3 is a weak base. So remember, weak bases are going to look like ammonia or things like C3NH2 or CH3CH2NH2 or other combinations, but you're always going to see that nitrogen in there. Okay, that nitrogen corresponding with other carbon and hydrogens is always going to be a weak base. All right. So this is a weak base. So what does that tell you about this ion? It's a weak acid. Okay. And then you look at Br minus, and for Br minus, you're going to say, okay, it's the conjugate base of what acid? It's the conjugate base of HBr. HBr is a what? Strong acid. So Br minus is neutral. Are you with me? So if I have a neutral anion and an acidic cation, then the compound itself, right, is what?
Acidic.
Acidic, basic, or neutral?
Acidic.
Acidic. Okay. So this first one's acidic, yeah? All right, let's look at the next one. Some of you got this, but a number of you do not quite have this concept yet. So let's just go through each of these one last time here. K plus, I minus. We're checking the cation to see if it's acidic. It is the it is a group 1 or group 2 metal ion, right? And we know that group 1 and group 2 metal ions are the counter ions of strong bases. So if it's the counter ion of a strong base, it itself is what?
Neutral.
Neutral, right? It's neutral. And then I minus is the conjugate base of the strong acid HI. So what can we say about I minus?
It's neutral.
It's neutral as well, right? And if the cation is neutral and the anion is neutral, then Ki is
Neutral.
neutral. All right. Now this one, Al3 plus is the cation and C2H3O2 minus is the anion. Okay. Al3 plus, ding, 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 small highly charged metal, right? So what do you know about small highly charged metals?
Acidic.
Acidic. All right. C2H3O2 minus is the conjugate base of HC2H3O2. HC2H3O2 is acetic acid. It's a weak acid. So what can we say about that?
We can't tell.
We can't tell for the anion. You can't tell for the compound, but what can you say about this anion?
Basic.
Weak base, right? This is a weak acid, this is a weak base. So now together, you can't tell with more information, without more information. You'd have to compare the value of Ka to the value of Kb for these, okay? Whichever one's bigger, that's the one that would dominate. Okay, Fe3 plus, NO3 minus. Fe3 plus, ding, 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 small highly charged metal. So what is it?
Acidic.
It's acidic. It's a weak acid, right? NO3 minus is the conjugate base of HNO3. HNO3 is a strong acid, so NO3 minus is
Neutral.
neutral, right? So what can we say about this compound?
It's acidic.
It's acidic, all right? This is asking which one is most likely to be basic, right? Okay, so let's get to the last one, which is the right answer. Li plus and F minus. What can we say about Li plus?
It comes from a strong base.
Comes from a strong base, so it is neutral. Right? So weak bases, let me go back. Let me go back because maybe that's part of the issue. This PowerPoint is a little bit finicky, and so it might take me a minute. Remember when we talked about weak bases last time? Where was my table? Oh, I passed it. Maybe this was a mistake. Come on, wake up. Whew. All right. This is the table of some weak bases, okay? And you want to identify them in a couple of ways. If they have this nitrogen, right? So ammonia, ethylamine, methylamine. Notice they all have very similar structure. They're hydrocarbons with nitrogen, okay? So whenever you see a hydrocarbon with nitrogen, you know that's a weak base. The other important weak bases are the bicarbonate ion and the carbonate ion. And of course, there's still a lot of other weak bases that we're talking about here, which are ions, right? But these are important enough that they made the table, okay? But there are other ones as well. But these guys, how do you recognize weak bases? They're basically derivatives of ammonia. Okay, so they're going to be either ammonia itself or a hydrocarbon with nitrogen. That's how you recognize them. Can you hear me? I hate that. In and out. Do you mean like the hamburger stand? This is like the kind of thing where like I have no idea what to do. What do you do when this happens? I'm just gonna hope it gets better. 5 guys. All right. Okay. All right. Let's go on. If you missed that last question, hopefully that you understand a little bit better. But if not, there's a pre-lecture video on that, right? Was it? I think it's one from today, though, right? I think it's a pre-lecture video from today. If you didn't watch it carefully enough, maybe go back and review that. All right, and it'll explain that a little bit better. It's super important to understand that concept because we'll be dealing with it a lot. Okay, now the next question is, well, once I recognize something as a weak base or a weak acid, how do I find its, Once I recognize an ion that acts as a weak base or a weak acid, how do I determine the pH of a solution containing that ion, right? Normally, to find the pH of a solution of a weak base or a weak acid, we work an equilibrium problem, and we need the value of Ka or Kb. So it's exactly the same, except the values of Ka and Kb for those ions aren't tabulated. We have to get it from the value of Ka or Kb for its conjugate. Okay, so the important equation here is this one. Ka times Kb is always going to be equal to Kw. What that means is if I know the Ka for a weak acid, then I can get the Kb for its conjugate base from this equation. Kw, remember, is 10 to the minus 14. All right. Another way I can write this equation is pKa plus pKb is equal to 14. All right. Those are equivalent. And I think it'll just be easiest to work an example. So let's do that. We want to figure out the find OH minus concentration and pH of a solution that is 0.250 molar sodium bicarbonate. Okay. And notice that they give me Ka for H2CO3 is 4.3 times 10 to the minus 7. All right. So the first thing we have to do is say, aha, they're asking me to find the pH of an ionic compound. So what am I dealing with here, right? Is it a weak acid? Is it a weak base? Is it pH neutral? Right, so that's the first question you have to ask yourself. And again, we have to go through this process where we look at the cation and we look at the anion. In this case, the cation is Na+. What do you know about Na+? Acidic or neutral?
Neutral.
Neutral,
Neutral.
right? Na+ is neutral. What do you know about HCO3 minus?
Would that be basic?
That'd be basic, right? Because it's the conjugate base of the weak acid H2CO3. Okay? And notice they're giving you Ka for that conjugate acid. So, how do you find the pH of a weak base solution? We call up our best friend, B plus H2O in equilibrium with OH minus plus BH plus, right? That's one of our two best friends, right, equations. So now we're going to apply that equation to the HCO3 minus ion. And we get this equation, right? Okay, so notice this is an equation for a weak base, right? How do you find the pH? You got to work an equilibrium problem. You got to set up an ice table, right? So we set up our ice table. What's the initial concentration of HCO3 minus?
.25.
Correct. Correct. 0.250 molar, right?
Wait, is there a reason why it says there's a sodium 0.25 molarity?
Because remember, these ions don't exist on their own, right? I can't just have a solution of HCO3 minus. It's always with a counter ion, right? If I just had a solution of H3O3 minus, right? Craziness. It's like a thundercloud, right? You can't have beakers of negative ions by themselves. You can't have beakers of positive ions by themselves. They're always going to be paired with a counter ion. So you're always going to have ionic compounds that are charge neutral, and one of them might be acidic or basic, right? So in other words, when I have NaHCO3, that ionic compound, when it goes in a solution, what does it do? It completely dissociates into Na plus aqueous plus HCO3 minus aqueous, right? And it's this HCO3 minus, right, that then acts as a weak base. Are you with me? All right, so 0.250 molar 0, 0, minus x, 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 0.250 minus x, 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 right? So then this is the equation, the equilibrium constant for this. Still breaking up? Can you hear me?
Yeah, I think we just kind of missed the question about the KB that you asked.
Right. Okay. So the KB for this, the equilibrium constant for this equation, right, is equal to the concentration of OH minus times the concentration of H2CO3 divided by the concentration of HCO3 minus. Yeah, does that make sense?
Yeah.
So
So is it x squared over
exactly,
0.25 minus x?
exactly right. Okay. Now, to solve this problem for x, what do I need? I need KB, right? But what did the equation give me? Ka for the conjugate. It'll always be that way, right? You're not going to find tables of Ks for ions acting as acids and bases. Okay? But you will find Ks for their conjugates. All right? So, given that I know Ka, I can get Kb, right? Because I just said Ka times Kb is equal to Kw, right? So, Ka times Kb is equal to 10 to the minus 14. Ka is equal to, so Kb, sorry, is equal to 10 to the minus 14 divided by Ka is equal to 10 to the minus 14 divided by, there's Ka, right? So I'm going to plug that in there. 4.3 times 10 to the minus 7, right? So Kb comes out to be equal to 2.32 times 10 to the minus 8. Okay? So that is going to go into there, right? And I got to solve that for x. So I'm going to get something like this. X squared over 0.250 minus x is equal to 2.32 times 10 to the minus 8. Okay. So what do you think? Can I make the x a small approximation?
Yep.
Yep, because that's a pretty small number. So I can make the x a small approximation. I solve that for x. X comes out to be 7.6 times 10 to the minus 5. Okay. Now I go back to my ICE table and I see that X is equal to the concentration of OH minus. So that's equal to the concentration of OH minus. That's one of the things it was asking for, right? So there's one of my answers. The other thing it wanted was pH, right? There's a couple of ways you can do that. The easiest way is to find pOH. When you know OH minus is minus the log of 7.6 times 10 to the minus 5. So pOH is equal to 4.12. And then you know that pH plus pOH is equal to 14. So pH is equal to 14 minus pOH is equal to 14 minus 4.12, which is equal to 9.88. So does that make sense? So notice this problem is very, very similar to problems we've done before, right? It's basically asking you to find the pH of a weak base, right? Whenever you got to find the pH of a weak base or a weak acid, what do you got to do? You got to work an equilibrium problem, right? Set up your ICE table, right? This is the weak base equation right here. It'll always be that, right? A version of that. Set up your ICE table, Solve for X. In order to solve for X, you need KB. The only difference in this problem and the other weak base problems that you've already done is that you don't know KB right away, right? It's KB is not given. You got to get KB from KA. I'll just repeat everything twice. Will that work? You get KB from KA, all right? And this little handy dandy relationship right here, KA times KB is 10 to the minus 14. Okay, so that's the only difference in this problem and other problems that you've already done. All right, good. Why don't you try one? Okay, let me, this will take a couple minutes, so go ahead and start it. I'm going to start the poll. There you go. Try it. Try this kind of problem. This kind of problem is super important that you be able to do it. So try it. Just in case you're having trouble getting started, let me give you a little hint. Okay. Sodium benzoate is an ionic compound. I'm just going to write it as Na benz, right? Where benz is just the anion. It could be any anion. You could have any structure you want. It's not giving us the structure, so I don't have to worry about it. Okay. So Na plus, of course, is pH neutral. So benz minus is the conjugate base of this weak acid, benzoic acid. All right. So what equation do I need to write to start my ice table? Well, it's benz minus plus H2O in equilibrium with OH minus plus H benz. Right, or benz H plus, however you want to write it. Okay, H benz is more typical in this case, but it doesn't matter. You can write it either way, right? So the next thing you want to do is set up your ice table, right? And then remember, this is an ion acting as a base. They're giving you Ka. To solve this problem, you're going to need KB, right? So how are you going to get KB? KA times KB is equal to KW. So KB is equal to KW divided by KA is equal to 10 to the minus 14 divided by KA, 6.5 times 10 to the minus 5.
Can I ask a clarifying
Of
question?
course. Yep.
So we're using the weak base equation because sodium benzoate is a weak base because sodium is in it. Is that how we know that?
Well, sodium is the cation. And what do you know about sodium? It's neutral, right?
Uh-huh.
It's the counter ion of sodium hydroxide. Sodium
Right.
hydroxide is a strong base, so sodium is neutral. Benzoate, the benzoate ion, which we don't know have the formula for or anything, but we know that it's the conjugate base of benzoic acid. It's because it's given here in the problem, right? This is benzoic acid, and that's the conjugate base. So we know that it's the conjugate base of a weak acid because benzoic acid is not a strong acid, right? So therefore, benzoate is a weak base. So that's why we're using the weak base equation.
Okay.
Does that make
Thank you.
sense?
Yeah, it does. Thank you.
I have a quick question.
Yeah.
So when it comes to writing out the formula, it doesn't really matter if we know the formula or not for the sodium
Correct.
benzoic acid.
Correct.
Okay.
Doesn't matter. They're all gonna be, all of these are gonna basically be of this form, right? All weak acids are gonna be HA plus H2O, H3O plus A minus, right? All weak bases are gonna be B plus H2O in equilibrium with OH minus plus BH plus. Right, so these are these two equations, right? You don't really even need to know what A minus is. You don't need to know what B is. They just act the same way every single time.
So we just have to really work off the moles that the solution is given, and then we can get everything else.
Right, the concentration that's given would be the one that goes here, right?
Yeah. Gotcha. Thank you.
Yeah. This is awesome, by the way. A lot of you are getting this correct. So this is not an easy problem, but a lot of you are getting it correct. So good job.
So then if you determine that this was a strong base, you wouldn't need to do the ice table because you would be able to calculate it because it'd be the exact amount that you have, right?
Correct. Strong base. If it's a strong base, like if it would be 0.250 molar NaOH, right? Then you know that the OH minus concentration is 0.250 molar, and you're done. You can just take POH of that and subtract from 14, and you're done.
Perfect. Okay, thank you.
Okay, I'm going to give you guys another 10 or 15 seconds here if you can try to finish up. But this is fabulous. I'm going to end it here. The right answer was B, and look at that. 3/4 of you got the right answer. So great job. So what you do, just for those of you that didn't get it right, you have 0.250, right? You have 0, 0. It goes to the right. So this is minus x, x, x. So 0.250 minus x, 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 right? So you have x squared over 0.250 minus x is equal to KB, right? And now you got to get KB this way, right? So KB turns out to be 1.5 times 10 to the minus 10, right? So you make the x a small approximation, right? You can do that, right? Because look at how small KB is. So x squared is equal to 0.250 times 1.5 times 10 to the minus 10, right? And x turns out to be equal to 6.1 times 10 to the minus 6. And of course, x is equal to the OH minus concentration, right? So that's equal to the OH minus concentration. If I take minus the log of that, that gives me POH. So POH comes out to be equal to 5.21. And so pH is equal to 14 minus 5.21, which is equal to 8.79. Okay. Good job, guys. Nice. All right. Any questions on that? Okay. The last Lewis acids and bases I'm not going to cover. That won't be on the exam either. But I do want to talk for a minute about polyprotic acids. So there are some acids that have more than one proton. So a normal acid, right, HA, a normal polyprotic acid, right? We know this equilibrium constant for it. I mean, this equilibrium expression for it, right? A polyprotic acid would be something like H2A. And polyprotic acids usually ionize in 2 steps. So here's step number 1. And the second step is just the same thing again, but with this one. HA minus plus H2O goes to form H3O plus A2 minus. Okay? And to get the pH of a solution of a polyprotic acid, except for H2SO4, from first step only. Okay, except dilute H2SO4 solutions, which we will not be doing in this class. Okay, we won't worry about that. All right. So in other words, for a polyprotic acid, just treat it like a weak acid and look at the first step, and that's all you got to do. Right. So just work an equilibrium problem for the first step. Usually you'll have Ka1 and Ka2. Okay. all you have to do is worry about is Ka1. So here are some examples of some weak acid, of some polyprotic acids. Sulfuric acid is kind of interesting. It's the only one like this. It's strong in its first step, but weak in its second step. All right, so remember, sulfuric acid was one of the 6 strong acids. If you're trying to figure out the pH of a sulfuric acid solution, just treat it like a strong acid, but only worry about the first step, right? So for example, if I have a 0.1 molar H2SO4 solution, right? And I want to know the concentration of H3O plus, it's equal to 0.1 molar. It just acts like a normal strong acid, all right? And I don't really have to worry about that second step, except in really dilute solutions, which we won't be dealing with. Okay. Here's some other polyprotic acids. You might recognize citric acid. This has actually 3 ionizable protons, so it'll ionize in 3 steps. Ka1 is this, Ka2 is that, and Ka3 is that. Okay. Again, if you're figuring out the pH of these solutions, you just have to worry about Ka1. All right, in the first ionization step. Here's why. Let's say I have this solution, right? If I figure out the contribution of H3O plus from that step, it's 2.8 times 10 to the minus 3 molar. If I then go on and solve an equilibrium problem for the second step, look at how much it adds. 10 to the minus 12 molar. What's 2.8 times 10 to the minus 3 plus 1.6 times 10 to the minus 12?
Basically 2.8 times 10 to the negative 3.
Right, it's just 2.8 times 10 to the minus 3, right? Because it's like adding, this is like 0.0028, and this is like 0.000000000 something, right? So when you add these two numbers together, that's like weighing yourself with and without a penny in your pocket. It's not going to make any difference. Okay, so the second step is completely negligible. Okay, that's it. We finished our chapter on acids and bases, and you should have everything you need now to complete the problem set. Next week, we continue with our last week of equilibria. Remember, I told you we have a few weeks of equilibria, so next week will be the last week. We're going to look at buffers, all right? And buffers are systems that resist pH change. So we'll be looking at those and working with those. And working with those is going to require us to put together everything that we've learned in the last couple chapters. Okay? So that's why I'm saying this material is really cumulative, all right? And we're building on what we know gradually, right? Like you couldn't solve this kind of problem unless you knew how to solve a weak base equilibrium problem, right? And then we add another little wrinkle with the Ka times Kb. So we'll be continuing that pattern, okay? All right, thanks all. I really appreciate it. And I hope you have a good afternoon. I will, of course, stick around here and answer any questions you might have, but I'm going to go ahead and end class here and see you all next Monday. Okay? Bye.